In the previous lecture, we've seen through two examples how we can apply the principle of conservation of energy, that is the first law of thermodynamics, for a control mass to an open system or a control volume system. And we've seen this through example of steady state operation of two open systems. The first one was a throttling device and second one was a compressor. In this lecture, we are going to extend our discussion and provide a complete derivation of the mathematical formulation of the first law of thermodynamics for a control volume system. Before we go into the derivation, we first begin with the principle of conservation of mass. So in the previous example of the compressor that we discussed in the last lecture, we saw that before we can apply the conservation of energy principle, that is the first law, to an open system, we must also apply the principle of conservation of mass. That means whenever we analyze an open system, then we also have to take into account the conservation of mass along with the conservation of energy. So let's begin by discussing the conservation of mass, and to do so, let's consider a general control volume system. So let's say this is an open system with one inlet and one exit. So we'll denote the inlet by I and exit by E. So this is an open system, so we'll analyze it using a control volume approach. So this dashed line is the control volume that we are interested in. So this is my control volume, and the boundary of the control volume is called a control surface. Through this control surface, mass can enter and exit the control volume. And let's say the mass flow rate at the inlet is m dot I, and the mass flow rate at which the substance exits the control volume is m dot subscript E. Now, to apply the conservation of mass for the control volume, we can start with a control mass. And note that control mass is a system through the boundaries of which there is no mass transfer. That means mass of a control mass system remains the same. Therefore, let's consider a control mass again using, let's say, denoted by these virtual pistons. Essentially, these virtual pistons separate the control mass from the surroundings, and these are the boundaries across which no mass transfer can take place. So at time t, we'll say that the piston at the inlet and the exit are at these locations. That means there is certain volume between the control surface over here and this piston at the inlet at time t, whereas at time t plus delta t, this piston moves and touches the control surface, whereas the piston at the exit moves away from the control surface, and there is a volume enclosed between this piston and the control surface at time t plus delta t. Now we can apply the principle of conservation of mass. So note that what we mean by the principle of conservation of mass for a control mass system is that the mass of the control mass at time t is equal to the mass at time t plus delta t. Now let's look at what is the mass of this control mass system at time t. So there are two contributions to this mass of this control mass system at time t. First is the mass of the substance enclosed within this control volume, that is within this volume enclosed by the control surface, and this mass that is enclosed between the piston at the inlet and the control surface. Therefore, mass at time t can be written as the mass of the substance enclosed within the control volume at time t plus this particular mass, which we'll call as delta mi. So delta mi is the mass of the substance that is displaced by this virtual piston at the inlet from time t to delta t. Note here, in our derivation, we now do not assume that mCv, that is mass within the control volume, is not constant, because for an unsteady process it may change with time, and this is equal to mass of the control mass system at time t plus delta t, which will be equal to the mass of the substance enclosed in the control volume at time t plus delta t plus, now we do not have any mass of the substance between the control surface and the inlet because the piston is touching the control surface at time t plus delta t. But here within this volume there is some mass, and we'll call it as delta me. So this is the mass that is enclosed within the volume bounded by the control surface and the piston at the exit, as this control mass transforms from time t to t plus delta t. Now, because the mass of substance within a control mass remains fixed, because we know that there's no transfer of mass across the boundary of a control mass or a closed system. Therefore, this left hand side is equal to the right hand side. So we can rearrange this equation as follows. So we can take the control volume terms on one side and the other terms on the other side. This gives us mCv at t plus delta t minus the mass within the control volume at time t is equal to delta mi minus delta me, and we can divide this equation on both sides by delta t, that is the time interval from time t to t plus delta t. Now, in the limit that delta t tends to 0, let's look at what this equation simplifies to. So in the limit that delta t tends to 0, you can see that this particular term over here is in fact the time derivative of the mass within the control volume, and that is equal to, so we have limit of delta t tending to 0 of delta mi over delta t, and that is equal to the mass flow rate at the inlet, and this term in the limit that delta t tends to 0 is the mass flow rate through the exit. Therefore, the statement of conservation of mass for a control volume is given by the rate at which mass is accumulating within the control volume is equal to the net mass inflow into the control volume, and the net mass flow rate into the control volume is the mass flow rate into the system through the inlet minus the mass flow rate out of the system through the exit. Now, we can generalize this result if we have multiple inlets and outlets. Then we can write dmCv dt, that is the rate of change of the mass of the substance within the control volume, is equal to the summation of mass flow rates through various inlets minus summation of mass flow rates through the exit. So in the diagram over here, we considered only one inlet and one exit, but if we had multiple inlets and exits, this is the equation that we are going to get, and this is the conservation of mass for a control volume. Note that we started with the principle of conservation of mass for a control mass or a closed system, and we extended it to a control volume. Similarly, we are going to do it for the principle for conservation of energy, that is the first law of thermodynamics. Now, as we have seen in the previous lecture, if we have steady state, then this dmCv dt, that is the left hand side, is going to be 0 because there's no change of any property within the system. Therefore, we'll have that the mass flow rate, the total mass flow rate through the inlet is equal to the total mass flow rate through the exit of the control volume, and this will be for a steady state. However, for unsteady systems, this is the equation that we're going to use. So now that we have applied the principle of conservation of mass to a control volume, we can now look at the first law for the control volume. So whenever you do thermodynamic analysis for a control volume, you have to apply both the conservation of mass as well as the first law, that is conservation of energy. And note that for a closed system, we don't need to apply conservation of mass because given the fact that there's no mass flow rate through the system boundaries, for a closed system or a control mass, the mass is always conserved. But we need to apply conservation of mass for control volume because there's mass flow rate through the system boundaries. Now let's consider a similar general open system with, as of now, let's consider only one inlet and one exit. Denoted by I and E respectively. So this is the open system that we are interested in, on which we'll apply the first law. The control volume is denoted by this broken line, and this is in fact the control surface, and the volume enclosed by this control surface is the control volume. Now let's say this is some system. This could be a compressor with gases flowing in and out on which we do work, and there could be heat transfer. and this could also be a turbine. So this is any general system with one inlet and one exit. So let's say that work is done on this open system at a rate W dot CV, and heat is transferred to this control volume at rate Q dot CV. So what is this? Let's say Q dot CV is, in fact, let's say if you add heat delta Q CV to this system over time t to t plus delta t, then Q dot CV is defined as this delta Q CV by delta t in the limit of delta t tending to 0. Similarly, the time rate of work, which is the power, is given by limit of delta t tending to 0, delta WCV by delta t. Here delta WCV is the work that is done on the system from time t to t plus delta t. Now, just as we applied the first law to a compressor in the previous lecture, we'll apply the first law to this control volume, starting with a control mass, because we know for the control mass the first law is given as the change in energy of a control mass system is equal to the heat that is transferred to the system plus the work done on the system. So we know this equation, and from this equation we need to derive the first law for a control volume. So to do so, let's identify a control mass. So again, let's consider this virtual pistons at the inlet and the exit, and anything enclosed within these pistons and this boundary of the system is my control mass. Now this is the position in yellow color of the pistons at time t. So there is certain volume enclosed between the piston at the inlet and the control surface at time t, while the piston at the exit is touching the control surface. And note that these are virtual pistons. These are essentially some virtual boundary of a control mass that we are tracking as it is flowing through this control volume. So this is the position at time t. At time t plus delta t, these pistons move. So the piston at the inlet touches the control surface at time t plus delta t, whereas the piston at the exit moves away from the control surface, and its position is shown over here. Now we know the state of the system at time t and t plus delta t, and we need to relate those states of this control mass system using the first law, and that is straightforward application of the first law for the control mass, that is given by the change in energy, that is total energy at time t plus delta t minus change in energy at time t, is equal to, so within this time interval we do delta W work and delta Q heat is transferred to the system. Now let us look at the terms on the left hand side. So energy of this control mass system at time t is equal to the sum of energy of the working substance within the control volume and this volume over here. Therefore, we can write the total energy of the system is energy of the control volume plus, let's say, this mass is delta mi. So we have delta mi times the specific energy at state I, that is at the inlet. Similarly, energy of the control mass at time t plus delta t is ECV t plus delta t, because now we are not having a steady state, so the energy within the control volume can also change with time. Plus, this is the mass of the substance enclosed between the piston and the control surface, and that is delta m E times the specific energy at the exit conditions is the energy of this mass enclosed between the control surface and the piston at the exit. Using these two values, we can simplify or we can expand the terms on the left hand side of this equation. Now let's look at the work that is done on the system while transforming this control mass from time t to t plus delta t. So the work done, delta W, has two contributions. One is the work that is done on the control volume, this part, over time t to t plus delta t. And the second contribution is due to flow work. Recall that flow work terms come into picture because we have to move these pistons to displace this gas or reduce the volume of the gas at the inlet and expand the gas at the outlet. So to do so, we have to do this much work, that is minus P delta V. So at inlet, pressure is Pi, so minus Pi times delta V. So what is delta V? So at time t plus delta t, our volume is 0 between this control surface and the piston, and at time t, it is delta mi over the density at the inlet. Similarly, we have this work done to move the piston, so that is minus P2 times the change in volume, which is delta me over the density at the exit minus 0, because initially the volume was 0. Therefore, the net work that is done on this control mass from time t to t plus delta t is given by this. Note that this is pressure at the exit. Another thing to note is that in this particular derivation, we are not assuming the system to be in steady state. Therefore, over time t to t plus delta t, different amount of mass can enter the system and different amount of mass can leave the system. That means there could be mass accumulation or mass depletion within the control volume. Therefore, delta mi and delta me are different in this particular case. So this is the total work that is done, and we call that these PV terms, pressure times specific volumes, correspond to the flow work. Now we can substitute this equation back into the first law and these equations for energy also in this first law. So if we do so, this is what we get. So first we'll have the difference between these two terms. So we have the difference in the total energy of the substance within the control volume at time t and t plus delta t, then the difference between these two terms, so we have delta me ee minus delta mi times the specific energy at the inlet conditions. So this whole term is equal to the difference in the energy of the control mass at times t plus delta t and time t, and this is equal to delta q, and let's put a subscript cv because this is the heat that is added to the control volume. Then we have these terms for work on the right hand side, and these terms are delta w cv plus delta m I corresponding to the inlet, so this is the flow work corresponding to the inlet, and exit. Next, as we did in the previous lecture, we'll club these terms with the energy terms on the left hand side. So what we get is so this is what we get after rearranging the terms in this equation. Now let's divide both sides of this equation by delta t. And let's take the limit of delta t tending to 0. So if we do so, what we'll get, the first term is the time derivative of the change in total energy within the control volume plus, so delta m e by delta t in the limit delta t tending to 0 is the mass flow rate through the exit, so that is m dot e times the specific energy plus PEVE, that is the flow work, minus the contribution for the energy that is coming in through the inlet, and this is equal to, so recall that this term in the limit delta t equals to 0 would become q dot cv, and this particular term would be w dot cv, and the rate at which heat is being transferred to the control volume and the work is being done on the control volume. These rates in general are not constant, they may be a function of time. Alternatively, we can write this equation as, so if we take these two terms on the right hand side, so we can put an equality sign over here, and this is minus over here. So therefore, we can write the first law for a control volume for a single inlet and exit as the change in the energy of the working substance within the control volume is equal to the rate at which energy is transferred to the control volume, so in various forms. So let's look at it in more detail. So the term on the left hand side is the rate of change of energy within the control volume, and this rate at which the energy within the control volume is changing is equal to the rate at which we are supplying energy, and that is in form of work and heat, and due to the inlet, that is mass flow into the control volume and mass flow out of the control volume. So this is the general principle of conservation of energy applied to a control volume. Finally, now we can expand the energy in terms of the internal energy and potential energy, and as we did in the previous lecture, so we have, this is UE, that is the specific internal energy at the exit conditions, plus the kinetic energy term and the potential energy term. Similarly, so this is the specific energy at the exit conditions, this is the specific energy at the inlet conditions, which is sum of the internal energy, kinetic energy, and the potential energy. So if we plug in these values over here, we'll see that again we can club these internal energy and the flow work terms and define this, the sum of these two, in terms of enthalpy, that is He. Similarly, we can combine these two terms and define this sum in terms of the enthalpy at inlet conditions. If we do so, the equation can be written in this form. That is, the rate of change of energy within the control volume is equal to the rate at which we do work on the control volume, the rate at which we supply heat to the control volume, plus this contribution due to inlet and exit of the mass into and out of the control volume. So this is the energy carried in by mass flow into the control volume, and this is the energy carried out by the mass flow exiting through the control volume. And now we have this enthalpy term, that is due to the sum of internal energy and the flow work, and we also have the kinetic energies and the potential energy terms. And for this derivation, we started off with a control volume with single inlet and single exit, but we can generalize it, so we can do summation over all inlet and exits of an open system. Finally, let's see what is this term. So if we have an open system, then the properties within this control volume can change spatially, and of course they are changing over time. So the total energy, so at every point you will have the total specific energy of the substance, and the total energy within the control volume is this density times the specific energy, and we'll do a volume integral over this energy per unit volume. So this is energy per unit volume. So this is our total energy within the control volume. Now in this equation you see that always these kinetic energy and the potential energy terms will always appear along with this specific enthalpy. Therefore, to write this first law for the control volume in a shorter notation, often it is convenient to introduce these new terms. The first term is called the total enthalpy. In particular, the total specific enthalpy, and that is this sum of all these terms. So we'll say this total enthalpy, which will denote by H subscript TOT, is equal to H, the specific enthalpy, plus the kinetic energy per unit mass plus the potential energy per unit mass. So this is the definition of total specific enthalpy. Sometimes we also come across a term called stagnation enthalpy, and this term stagnation enthalpy is widely used in compressible fluid flow. So what stagnation enthalpy is, so we'll denote by H subscript. Stag is enthalpy plus the kinetic energy. So if we want to write this equation, that is the first law applied to a control volume, in terms of the total specific enthalpy, then we can get a very simple form of this equation. So we get dECV by dt is equal to W dot CV plus Q dot CV plus summation over m dot inlet times the total enthalpy at the inlet conditions minus summation over all the exits of m dot times the total specific enthalpy at those exit conditions. So this is the most general form of the first law for a control volume, and for this derivation we've not assumed steady state, so we can this equation applies to unsteady systems as well, with multiple inlets and multiple exits. Now you can go back and see that if we have steady state, then the left hand side would be 0, and we'll recover the equation that we had derived last time for a compressor. And in the next lecture we are going to apply this general equation, the first law for a control volume, to many engineering systems, and we'll be able to simplify this equation for different engineering systems. As of now, we've already seen simplification of this equation in the previous lecture for two systems. One is a throttling device where we didn't have any work input and heat transfer, and it was in steady state, and that's why we had got that for a throttling process we had got that H total at inlet is H total at exit, and if we neglect the kinetic and potential energy terms, which we did that time, we get that throttling process is an isenthalpic process. And we've also seen the case of a compressor working at a steady state. In that case, this left hand side would be 0, and we can relate the inlet and exit conditions with the rate at which work is being done on the system and heat is being transferred to the system. And we'll discuss more simplifications of these equations to different engineering systems in the next lecture.